we'll see how that goes. Okay, so our plan is to do, we have a little bit of administrative tasks to do first. So is everyone okay at 1 p.m. Today, obviously, Friday, then Monday, Wednesday, Friday, and we're done. But that means it's going to be intense for assignments. I'm assuming that the day after the course, you'll just be working on the assignment. That's what I'm guessing. I have 2 assignments, and last time I did a team assignment where everyone, you guys all work together as a group to solve one problem. And this was useful because there are let's say 2 physicists engineers, let's say 3 physicists engineers and 3 biologists, and I can throw a question at you guys and let you solve it. It's not a particularly difficult question, but it's a detail about a microscope. So the idea is that the biologists will know what they want. The physicists and engineers may know how to do the calculations, but if you work together, then I think you can share the task all together and complete everything in 2 hours. So that's what I did last time. The last 3 hours, the last lecture was actually one big problem that we solved as a team. So I was there, I will be there, and that also means everyone gets the same grade. Unless you guys are not happy with it. I don't see why you would not be happy with it. Because I know everyone here except Julien. Julien, I don't know so much, but I'm quite sure that that everyone will contribute to the team. So that's what I would suggest. So that would be 2 assignments and 1 big problem at the end that we do as a team. Does that make sense?
Yes.
Yeah.
Reasonable? Okay.
Absolutely.
Okay, so let me I had problems last time to get my slides to work properly. So let's see if this is solved. There was a new version of Zoom that came out today. So let's see. Imaging and share screen. Perfect. Dynamite. Okay, you guys can see my screen?
Yes.
Okay, good. So I'm gonna put this here. I can see everyone. And we can start as soon as this is ready. Okay, I can put this here. No. Yes, no, no. Okay. Let me get organized. All right. Okay. Good. Okay, and one last thing, so I can see my slides ahead of time and not look like an idiot. Yes, right here. Okay, I think I am finally in business. Okay, good. So the way this is going to work is that you should see the slides. You see my fancy laser pointer. Yes. Okay, good. And I'm gonna put this here. Okay, so our goal today is to discuss imaging. And we have objectives in this course. So there is a website, the regular website that we use with the university, the portal, the class portal. So there will be all the information available on the portal. And the objectives, we have the class is really 3 and 3. We have 3 biologists and 3 physicists, which is absolutely horrible for me, but we'll survive. And the objectives are not the same for biologists and for physicists. Because physicists and engineers, your goal will be to calculate. Okay, you will have to calculate things because that's your job. And for biologists, it's different. For biologists, you need to understand what is feasible and have an idea to do some simple calculations. So the goals are not the same, yet I'm still teaching to all 6 of you at the same time. So I will ask questions to biologists sometimes, and I will ask questions to physicists and engineers sometimes, and you may have to cross-explain to the other group. Let's say if I'm discussing wavefronts, it may be obvious to some of you, but maybe the biologists don't understand as much in detail. So then we will need to find an explanation. So in the course, as is described here, we need to understand all the essentials to manipulate light to make images. So the goal here is to make images, and to make images, we need to detect light and put everything together to make an imaging system. So that's really the goal of the current class. So we will not discuss other details that we will discuss in the other course after. So here, light will go through lenses. It's gonna hit detectors. It's going to be detected, but we're not going to discuss what happens to light when it goes into tissue, or when it excites molecules, or when fluorescence is emitted. So the interaction of light with material is only in the context of imaging, and not in the context of exciting materials and doing chemistry and biology in the molecules. Okay, so that's the first part. We need to understand that it's about imaging. And then the second is why are we giving this? Why is the biophotonics program giving this? Has an imaging course. We have an imaging course because we all work with imaging. Some of us build imaging systems, but some of us use imaging systems, and you need to know a minimum to be a useful scientist that uses the imaging system properly, or builds or modifies a system properly. So for everyone, we need to be able to make simple calculations to estimate if it is possible, if it's going to work, what's the limit. You know, that it's not about the details of how we make a perfect, or how we design a perfect system, but it's about making at least the right choices, or to understand if something is feasible or not feasible. And as I said before, biologists will learn to perform simple calculations, and physicists will learn more detailed calculations. Okay. Okay. Yeah. My Slack is active. Okay. And as I said, this is actually, I didn't have time to change the slides, but I was hoping that we would do one calculation as a group, and I will give you two assignments instead of here. I said two inverted classes for a project, but I think we should do one because it's a Zoom because on Zoom it's going to be a little bit more difficult. And then 2 assignments where you do all these simple calculations. Okay. So these are the objectives for the course. Okay. Notice that there are a lot of things that are the objectives are about understanding, and understanding is a very bad word for a course objective, because when are you done understanding? Well, never really.
Never.
So it's about really understand and explain, understand and explain, understand and calculate, name things, and get the index of refraction, for instance. So all these things, there is a component in the course that's about explaining to others. So if you're an engineer and you're talking about the index of refraction and you start saying a lot of things that are complicated to a biologist, then you're not doing your job. So explaining in a language that's understandable is important. It also works the other way. It's not just the index of refraction. If you talk about genetics and you try to explain genetics to an engineer and you use too many complicated words, you're going to get nowhere. So in all of the courses in the biophotonics program, explaining properly is part of the objectives. Okay, so you will see that there are a lot of things that are related to the basic of optics, but you've done quite a bit of it with Antoine. I got Antoine's slide. Who took the course with Antoine, by the way?
Me.
Yeah, Emile, no?
Nope.
Okay.
In fact,
Julien, I can't see you.
Yeah, I take
yeah.
it.
Okay. Okay. All right. I think I'll. Can I? 1, 2, 3, 4, 5, 5. Yeah. Okay. All right. So yeah. Okay. I'm assuming how did the course with Antoine go? Was it too fast? Too slow? Did you learn a lot? Did you learn very little? Well, what's the general feedback? No feedback?
Okay. Well, I feel it was more like a review of what we've seen in CEGEP.
Okay. And was the math?
With complex numbers in integrals.
Okay. And how, because I noticed that he was using a lot of math in his slides. So Vincent, Valérie, and Julien, how difficult was that? How unnatural was that? Was that too much math?
No, I think it was a good refresher from, again, things that we saw in CEGEP. So it was not too difficult, I would say. Yes, it demanded a certain adaptation, but it was fine, in my opinion.
Okay. Others?
I think it was okay. I didn't feel like it was too much.
Okay.
Well, there were a lot of equations in his slides, but we haven't used them all. It was just to show us the complexity sometimes.
Okay. Okay.
Yes.
All right. So I don't use much equations in general. I tend to leave the math on the side for those who actually need it. And I will poke Emile, Elahe, and Shadi, and a little bit Valérie, maybe, about some of the math, because Valérie likes math. But I will assume that you will be able to go get the information by yourself. So Emile, you have taken my optics class.
Yep.
Today's course, you'll notice that there will be a lot of things that are a refresher, but very quickly will fall into things that are not so much of a refresher. So I'll ask you to be patient for today, because we need to get people up to speed in basic imaging.
Absolutely no problem. It's been like 4 years, so
okay, good.
I'm not really. I could use a refresher.
Okay, well, that's all good. All right. So today, really, we'll start by just basic concepts that I know you've discussed with Antoine, but we'll do that fairly quickly. How many slides do I have? I have very few. I have 20 slides on the beginning, and then we'll be all set. So in 30 minutes, we'll be done with the general part. And then we'll fall into hardcore real imaging, and that'll be it. Okay, so let's get started. We all know that imaging is everywhere. There's no surprise there. We all use imaging in our projects. I usually have people explain what their projects are. I'm not. You may have done that with Antoine already, but I know Vincent is doing zebrafish imaging. Elahe is not doing so much imaging. She's analyzing spectra. Shadi, a little bit of imaging that's coming. Valérie, a lot of imaging. But I don't know about Julien and Emile. So do you guys want to tell us what your projects are? Do they involve a little bit of imaging?
Yeah, I work with quantitative phase imaging with a DHM, so a digital holographic microscope. And I try to not extrapolate, but calculate from the quantitative phase more useful biophysical properties such as thickness, refractive index, volume, and such.
And me, I'm using FLIM and two-photon imaging to study the impact of the matrix extracellular on the concentration on chloride ion in the neurons.
With Yves.
And Antoine.
Yeah, okay, good. All right, and I maybe do you, Elahe, Shadi, and Valérie, do you want to add something to what I said about you?
No.
No? Vincent?
Come again?
Did you want to add something to what I said about your project?
No, that's fine. Pretty simple.
Okay. So we all have our little, who's calling me? Not a good time. Okay. I don't know why. Okay. All right. So we all have our own little microscopes, and some of them want to see in 3D, some of them need to be fast, some of them need to be super precise, like Emile's. So they all have their specificity, and imaging has been at the forefront of developments in neurophotonics, because we want to see as small as possible. There was a Nobel Prize in super resolution a few years ago in 2014 in chemistry, by the way. But the STED and PALM methods that some of you may know are techniques that can go beyond the diffraction limit. So in our course, we'll learn about the diffraction limit. We'll see what that is. And then we'll see how some of these techniques go beyond these limits with clever tricks. And we always want to image as fast as possible. So there are techniques that will focus on speed. Some will focus on imaging as large as possible, and others will try to image as many things as possible. So we'll see the characteristics of all the all the microscopes that can improve on one aspect and push it further. Okay, so the first thing we need to start with to figure out where light is going in an imaging system is geometrical optics. So have you done, with Antoine, have you done some geometrical optics? What is it that you did with Antoine regarding geometrical optics?
We did a bit at the end.
Did
Okay.
a little bit
With
of
the three
lens,
rays stuff.
yeah. Lens work.
With with lenses?
Yes. A little bit of
thin lenses
calculations.
system.
Yeah, thin lenses. A little bit of calculations for like image distance, magnification, those kind of things.
Okay, and so so you've learned how to calculate where the image is for a certain object, for instance, for a simple lens.
Yeah.
So could you, if you had two lenses, would you be able to do it?
Yes.
Yeah.
Oh yeah, and any kind of combination of lenses?
Yeah, I think so.
Yeah. Okay. So how did you guys do that with Antoine? What equation did you use to calculate the position of an object and an image?
Well, like 1 over SO plus. Is that your question?
Yeah.
A plus 1 over SE equals 1 over F for one lens.
And so if you have an object and you know where it is, I'm assuming that all of you guys understand what we're talking about. We're talking about 1 over O plus 1 over I is equal to 1 over F, and then you calculate the distances. And that's very useful because if you have an object, you know where the image will be. But do you know what happens to light in between? So let's say you have an object that's 10 centimeters before a lens, and you'll know where the image will be, but you won't know what happens to the light in between, right? You'll just know, did we just lose someone? Did we just lose Elaine? Elaine, are you still there? Oh, we lost Elaine. Well, it doesn't matter. We're recording. She's going to come back. Okay. So you know where the object is, you know where the image is, but you don't know what happens to light in between. You only know, you only go from one object plane to one image plane. Say that again. It's refracted. Yeah, but
the lens.
Yeah. But the equations that you've used will only give you the light at the object plane and the image plane, nothing in between.
Yes.
So what I will show you is how to do everything in between. Okay? Because that's where we want to put our filters. That's where we want to have a big lens, a small lens. So we'll calculate everything to get the details right. Hello, Elahe, you're back.
Yeah, sorry, I was disconnected.
Oh, no problem. Okay, so the first part is geometrical optics. And what are the details of geometrical optics? In geometrical optics, we don't consider the wavelength of the light. So we have all used geometrical optics because we have worked with 1 over O plus 1 over I is equal to 1 over F. And in those cases, we trace rays. So we take a wave. We all know, and I know you've calculated waves with Antoine in his class. You've done a lot of things with waves. And then we take a wave and we replace it with rays. We consider rays instead of the whole wave because it's simpler. So in geometrical optics, it's easier to work with rays, and that's what we'll do. But we still need to understand the concepts, all the wave concepts that are associated with the rays. So that's what we're going to do for the next 8 slides. Okay, so geometric optics is a subset of optics because it does not consider the wavelength. So it does not consider diffraction, but it's easier. So let's get into that. You have seen, I know that you've seen Maxwell's equations with Antoine. You've all seen that. And the only thing that is important, these equations are complicated, okay? They have this operator here that's called the Laplacian, okay? It doesn't matter. The point of this, it's the important aspects of Maxwell's equations for everyone is to understand that when you have the equations, when you use all the equations, a wave is a solution to those equations. And that's really the part that's important. So there are many types of waves. And if you take a spherical wave, so you take an electric field that has this form. I know you've seen that with Antoine, but this is, what kind of form is this? So there's some amplitude, there's a term that oscillates, and there's a term in 1 over r. So this form here is what's called it's called a spherical wave. So we will not use the math. So don't worry about this, okay? You don't need to worry about this, okay? But the point is we have waves that we can consider as arising from a single point, and then they emit a wave in spheres or in circle in 2D around that point. So that's a spherical wave. Then we can also have a plane wave. So it's a wave that is essentially constant everywhere in space and has a wavefront that is a plane. So if I say wavefront, can anyone explain to me what a wavefront is? No? No one? No wavefronts? No?
I feel like
places of the wave that have equal amplitude.
Or equal phase.
Equal phase. So what's the phase? So we say, so we have a wave, and what's a point of a certain phase? What does that mean? Let's say if we use this, if we use this, okay? If we use this figure here, we have a wave, and I think that we all intuitively know that this will be a wavefront. But what does that mean, really? So Emile said it almost perfectly, but not quite. Your definition only works for a plane wave, what you said. So what is a wavefront? Why do we draw this line here? What is this? And can I draw the wavefront elsewhere? What's a wavefront? Valérie, you said points that have the same phase. What do you mean? How do you recognize points of the same phase on this figure here? So these, okay, this looks like it's a wavefront, and it's a wavefront because it's the same phase. But let's say if I draw here a line, is that also a wavefront?
I would say yes.
Okay, and who votes yes? Who votes no? Okay, so
yes.
it's yes. Okay, the points of the same phase is if we have a wave that is oscillatory like this, the points of the same phase are, for instance, the maxima. So the maximum here, this is a maximum, and if we were to look here, you know, underneath, we see that there's something that goes like this. So it's a maximum here, here. So they're all maxima. So these are all the same, they're all at the same phase, so it's a wave front. We can draw it anywhere, but by convention, we often just draw it at a maximum because it's convenient. Because if not, we would just draw lines everywhere. We could draw lines everywhere. We have the right to do that, but then we get lines everywhere, so it doesn't make much sense. So by convention, we have very often draw at the peak, and people will sometimes say the wave front is where the electric field is maximum. No, it's where the electric field has the same phase. So yes, at the maximum, that's true, but at a minimum, it's also a wave front. It's and even at zero, it's all the same phase. Okay, so if this is the wave front, okay, if we have the wave front here, what is a ray in this context? A ray is always perpendicular to the wave front, and that's what we'll use for everything else in geometrical optics. We'll use the ray instead of the wave front. Why do we do that? We do that because it's going to be so much simpler, because we can replace this thing that's everywhere in space by a single ray, and we'll calculate where the ray goes. Okay, so that's going to be our goal in today's class, to calculate where these rays go. Okay, so so a spherical wave has we say it's spherical because the wave front is a sphere around the point of the source, and a plane wave will have a wave front that's planar and has an amplitude that is constant. So the electric field everywhere in space is uniform. So there are other waves, okay? There are tons of solutions. All of these, there's a mathematical expression for these that if we go back to our equation here, if we take a plane wave like this and calculate the second derivative of this with respect to time, we multiply by this, and then we calculate this operator on this, this will be true. This will be equal to this. And for the spherical wave, it's also true. So we always talk about the spherical wave and the plane wave, but there are other waves. There are tons of other ways that can be described or that are solutions to this. And there's one that is particularly useful. Anyone has an idea what would that, what is, it's not a spherical wave. A spherical wave is coming from a point. So it's very useful in microscopy because we'll have a fluorophore, for instance, will emit light from a point. And a laser that's very far will emit a beam that's, let's say, mostly very large with a wavefront that's planar. But do you know another type of wave or another type of beam that, that is not a spherical wave or a plane wave?
Elliptical?
An elliptical beam? In what sense?
No, it's the wavefront is elliptical.
Okay, or if it's quadratic, elliptical, you know, if it was, we could say that a spherical wave has a wavefront that's curved. So tell me more. So tell me more.
Oh, elliptical.
So this here has an infinite, you know, it's an infinite wave. So it's everywhere in space. This one is very localized in space, but it has a curved wavefront. Can we have something that's in between? It's very common.
Could we have like a half circle, like for the two young slit experiment? Does that count?
Maybe.
Okay.
That's going to be in the double slit experiment. It would be really half a spherical beam, half a spherical wave.
Yeah.
But is there, if I say a Gaussian beam, does that ring a bell to some of you? A Gaussian beam? Yes? Valérie,
Yeah.
no?
Well, I've heard of it, but I don't remember.
Julien, yes, no?
I heard of it, so.
Okay, Elahe?
Yeah, I can imagine.
Okay, so
I know what Gaussian is.
So what is happening with a Gaussian beam? We had a spherical wave before, and a spherical wave had a circular wavefront, but a constant amplitude everywhere. Okay, it's constant, so the electric field is the same everywhere. But we can have a beam that has a wavefront that is curved like this, but an amplitude that is not curved, an amplitude that is not curved, I'm sorry, but not constant. So the amplitude goes from 0, or mostly 0, to a maximum and then a minimum. So you see that this is very different from a spherical beam, because a spherical beam has this curved wavefront, but it's a constant amplitude everywhere. The plane wave has a constant amplitude that goes from -infinity to infinity. So they're not really, well, the spherical beam is useful, but a beam that propagates is not infinite. So we will need to have some sort of a beam that is not infinite like a plane wave and not super punctual like a spherical beam. And that beam will be the Gaussian beam. And we will use that quite a bit in our calculations. Again, there is an equation for this. Okay, I could explain what this Gaussian beam is, but with an equation, but it's not useful. What we need to know is that there is an equation that expresses this this profile. So we can have a mathematical expression that will have, you know, some electric field as a function of space and time, and it's going to have some function that's going to be a Gaussian amplitude, and it's going to have some other component that's going to be a spherical wavefront. Okay? Some of you will do the math, some of you will not. Okay? Wow, super neurons, Valérie. So the point, again, is that this this Gaussian beam, if we replace that in Maxwell's equations, it's also going to be a solution for us for an approximation of Maxwell's equations. Okay, so there are a lot. What we recognize is there are a lot of solutions, and we don't want to have to solve the equations all the time. It's complicated. You know, even for half of you, I suspect that even the equations just look like a nightmare, and it may look like a nightmare to actually all of you, because I think they look like a nightmare to me. Okay, we don't want to have to solve differential equations all the time, and that's why we're going to be replacing the wavefronts by rays, and it's going to be good, but it's not going to be enough all the time. So then that's why we'll use this Gaussian beam, because it's going to be so close to something that's very useful, and it's also going to be much simpler to calculate than using the full Maxwell's equations all the time. Okay, so we're just setting the table here. Okay, so we're going to be working with these rays, but there is a link between the rays. The ray that we draw on a figure and real physics, okay? Because the ray is, have you heard of the Poynting vector with maybe with Antoine? Yes, no? Pointing vector, if I say pointing vector, no pointing vectors? Just a little bit? Okay. The pointing vector is the link between Maxwell's equations and ray optics, okay? So the pointing vector is something that's actually extremely easy to calculate. It's the cross product of the electric field and the magnetic field, and it gives some vector S by convention called the pointing vector. What is the pointing vector? The pointing vector is the energy per surface. So when you do calculations with waves and Maxwell's equations, and you're trying to see how much energy is flowing from one point to another through a surface, you'll calculate the pointing vector. That's how you can show that a wave is carrying energy, and you can show that an evanescent wave does not carry energy, because that's the Maxwell, the electromagnetic concept that is the key for energy transfer. So when we do ray optics, we're really tracing the pointing vector, because as you can see here, the pointing vector is the electric field cross B. So does this make sense to everyone, right? If I do vector cross B.
Yes.
Valérie? Yes, no?
Yeah.
Yeah, okay. So that means, you know, we do, you can see me, right? Everyone? Yeah, okay. So, so if you have an electric field in a given direction, and you have the magnetic field like this, then you'll have the pointing vector that's going to be according to the right-hand rule in a certain direction. So the energy flows in the direction of the pointing vector. Okay, so if we look at what we had before, if we have the wavefront, if we have a given wavefront here, where is the electric? If I have a wavefront that's like this, my ray is always perpendicular. And if the ray is perpendicular, that's because I have an electric field that is, let's say, going out. And if the electric field is going out, where's my magnetic field? Anyone would know on this figure? So if I have, whoops again. If I have, whoops again. Okay, if I have an electric field that comes out of the page, and I have a pointing vector this way. So if this is my electric field, where's my magnetic field?
It goes left.
This. Which way?
Left.
Left. Let's see. If I go with this, is it, so you say that it's going like this? Let's see. Oh, Lulu, je suis occupé, Coco. Je suis occupé. Oui, je le sais dans ton jeu, mais je suis occupé. Non, mais Coco, je suis occupé. Merci. Oui, je t'ai rendu super loin. Okay. So if we do E cross B, if the field is coming out of the page, then to get B, it needs to be in the other direction, in this direction. So E, B, then S. Okay, what was my point? Okay, what was my point?
What?
Say that again, Valérie. Okay, what?
You can do it that way too? I don't understand.
Well, okay, this is, when I draw this, that means the electric field is pointing outside of the paper. If I draw this, well, that means into the paper. Okay, good. All right. So, so yeah, I had a point here. What was my point? My point is that the ray here is the pointing vector, Okay, we'll consider it's the Poynting vector in our discussion, but in the more advanced books, that's not exactly what it is, but that's fine. Okay, so this is our Poynting vector, and the electric field and magnetic field will always be perpendicular. Okay, so that's what we have to remember. So that means essentially that the electric field and magnetic field will always be in the plane of the wavefront. Okay, so that's always true in space. Okay, in a wave, in an optical fiber, that's not true, but we don't have to worry about that for now. Okay, so we have our we're making this connection from Maxwell's equations to geometric optics, and the concepts of optics are the rays because we want to work with the rays, but this Poynting vector is actually very important, and I don't want to go too much in the details, but we need just one tiny little thing that we can't do with rays. We need to calculate the amount of energy that a wave has. Okay, we'll often have to calculate. I have a laser beam. You know, how much energy do I have? How many photons do I have? Because if we do one photon excitation, we know that one photon is needed to excite one molecule. So we'll need to know the amount of photons. So although we know that our vector is our ray, the value, the magnitude of that vector is really the energy, and the energy is useful to us. So I have 2 slides on this. Okay, a detail for the mathematically inclined people, but the Poynting vector is an instantaneous concept, just like the electric field and the magnetic field. But in a wave, we're interested in the average Poynting vector. So in a Poynting vector, okay, the biologists, don't worry too much about it. It's a Maxwell's equations detail, but the Poynting vector in a wave will go from maximum to half, to 0, to maximum, to half, 0, maximum. The Poynting vector keeps oscillating. When the magnetic field and the electric fields are 0, the Poynting vector is 0. So the Poynting vector will go from high, low, high, low, high, low, high, low very quickly during a cycle. And on average, it will be half of the maximum value. So when we want to calculate the Poynting vector of a beam, we're not interested in the Poynting vector, the instantaneous Poynting vector. We're interested in the average Poynting vector. And with a little bit of math, not much, we can calculate that the Poynting vector is essentially, think of that as the irradiance or the intensity. It's the power per surface, and it's essentially the square of the electric field. Okay, so if you know how many watts you have per area, you will be able to calculate the electric field. That's the key to multiphoton excitation. Okay, when we will discuss multiphoton excitation later, much later in the second class, so second course, well, at some point, you know, these nonlinear interactions occur because the electric field of the wave is really high. That's how we connect this to the physics of the molecule. Okay, but I was just wanted to say that for some of you. Okay, but everyone understands that if I have watts per square centimeter, can I change watts per square centimeter into something else? In photons, what do I do with watts? How do I convert watts to photons? What's a photon in terms, you know, what's the connection between watts and photons? Okay, what are the units of watts? Watts are something divided by something else. What's a watt?
It's a joule per second, I think.
Yeah, joule per second, energy per second. And what's a photon, really?
Energy.
Energy. So if I say watts per second or photons per second, that's the same, right?
Yeah.
So if I give you something that's 1 milliwatt, you should be able to calculate how many photons per second this means. Okay? All right.
One specific length of wave.
Yeah, exactly.
Wavelength.
For a specific frequency or a specific color, because the key is one photon is h, the Planck constant, times the frequency. So that's the energy of a single photon. What's the typical energy of a single photon? Typical. Just give me an order of magnitude. Let's say in joules. I'll take joules, although that's not my favorite. And I'll give you a trick right after that. Whoops. So in joules per second. So what's a photon approximately? How many joules? Okay, it's about 10 to the minus 19 joules per second, or approximately 10 to the minus 19. But there's a trick. Anyone knows the units of energy, electron volts? Does that? It's a high energy physics energy. It's a unit that's used a lot in high energy physics, and there's a reason why it's very convenient for us. Okay, first of all, it's the energy that a single electron will acquire when it goes from 0 volts to 1 volt. So it's extremely simple to understand. If an electron is accelerated by 100 volts, at the end, it has 100 electron volts of energy. So it's extremely convenient. Okay, and the reason why I'm talking about this now is that a photon at a wavelength of 1 micron has an energy of 1 electron volts. So 1 micron, 1 electron volts. It's just perfect. It's as if they were made to live together. Okay, so it becomes very, very, very easy to work with electron volts and to get an estimate, because you know that an electron volts is 10 to the minus 19 joules, and you know that a photon at 1 micron has 1 electron volt. So how much energy is a photon at half a micron? 500 nanometers.
Half an electron volt.
Nope.
Could you repeat?
Yeah, twice an electron volt. 2 electron volts.
Yes, 2 electron volts.
Of course.
So an electron volt at 1 micron, 2 electron volts at half a micron, and at 250 nanometers, 4 electron volts. Okay, all right. So it becomes, if you remember that, it becomes very easy to convert photon fluxes into energies. I always use 1 micron is 1 electron volt in all my calculations. It's so easy. I don't do H times C divided by lambda. Who does that? Who has the time? No. 1 electron volt, 1 micron. Okay. All right. Okay. So let's just see. Okay, because it is about this course is about getting an idea for numbers. You know, I used to teach the course more for understanding. you know, oh, let's try to discuss how we feel about this microscope and blah, blah, blah. But now I'm really trying to give you the tools to get numbers, okay? Because that's very often what we want. We want numbers. We want numbers to know, is this laser going to be sufficient? Should I buy this laser or this other laser? Or will I be able, with this crazy idea that I have, will I get enough fluorescence? Will I get enough light on my detector? So let's take a look at these photon fluxes. So a laser, okay, a typical, just a little crappy laser, a very ordinary laser, will give us 10 to the 26 photons per second per square meter. Okay, that's enormous. Okay, that's absolutely enormous. And if you look at the bright sunlight, which we do not look directly at, especially these days from inside the house, it's 10 to the 18. So it's already a billion times, essentially a billion times more intense than sunlight. Okay? And then if you go to the light from a star, okay, we're not doing astronomy, but in astronomy, they deal with light levels that are 10 to the 16 times lower than laser beams. So although astronomy is an imaging problem, okay, they're really just optics people, astronomers. They're just optics people wearing sandals, you know. But we're microscopists, so we live in we live in a very different world because we have 10 to the 16 times more light than them. Okay, so that's why we can't just say, oh yeah, astronomy, microscopy, that's the same. Well, it is technically the same, but at the level of details for how to detect, choose cameras, etc., then it's a completely different ballgame. Okay, and so what is 1 photon per second? Can anyone tell me what 1 photon per second is in watts? That's something that we'll need to remember a little bit. What's 1 photon per second? I'll try to calculate that in the meantime on a piece of paper. Whoops. Hey. So I need to know, get a piece of paper, calculate 1 photon per second.
Well, it's
which wavelength do we use?
Your pick.
All right.
Is it going to make a big difference?
No.
No.
It's pretty much 10 to the minus 19th watt per watt.
Uh-huh. So in joules per second, so that's 10 to the minus 19. What is that?
At one...
it's essentially 1 zeptojoule.
Zeptojoule. Okay.
So it's nano, pico, femto, atto, zepto. So 1 photon per second is a very small amount of energy per second. So if we go the other way, let's say we want to estimate 100 picowatts. What's 100 picowatts in photons per second? 100 picowatts. How do we calculate that? 100 picowatts per second. That's 10 to the minus 10 joules per second. And then 10 to the minus 10 joules per second. What do I do with that? I'll give you a trick. 10 to the 9 nanoseconds. Does that look reasonable? Is there 10 to the 9, 1 billion nanosecond in a second? Yes?
Yeah.
Okay. So I get 10 to the minus 19 joules per nanosecond. So what's that? According to what we just calculated before, it's approximately 1 photon per nanosecond. Right?
Yep.
How?
How?
Oh.
So 10 picowatts, okay, right here, 10 picowatts. So sorry, 100 pico. Pico is 10 to minus 12 watts per second. So multiply, I get 10 to the minus 10 joules. And then I replaced seconds by 1 billion nanoseconds. Here. So 10 to the 9 times nanoseconds is 1 second. Right? No?
Yeah.
So, because if I take 1 second and I say instead of 1 second, I'll say 10 to the 9 nanoseconds, that's the same thing.
Okay.
Because nano is 10 to the minus 9. So 10 to the 9 times 10 to the minus 9, that's the same. So then I get here, I get 10 to the minus 19 joules per nanosecond, and 10 to the minus 19 joules we know is approximately 1 photon. So 1 photon per nanosecond is 100 picowatts. I really like that number. It's a number to remember, okay?
Yeah.
1 photon in per nanosecond. If every nanosecond I get a photon, I have 100 picowatts. That's super useful. It's super useful. Because what is the, you can do the calculation for a PMT, but a PMT, okay, a photomultiplier tube, which we will see later, we will need to know that, but the detection limit of a PMT is approximately 1 photon per 50 nanosecond. So we'll see that a PMT can see picowatts, or a photon per 50 nanosecond. So we'll see that later. Okay, all right. That was we were just warming up with a little bit of math. The second thing we need to do, but only very quickly because we need to discuss lenses. It's right here. It's the index of refraction. I know you've discussed that with Antoine. You have discussed that with Antoine, right? Okay, so I will go very quickly. But what is the origin of the index of refraction in materials? What creates the index of refraction?
The velocity of light in vacuum.
It affects the velocity of light, but why is the light slowing down in a material? So there is an index of refraction. So the speed of light is whatever it is, but then we divide by the index of refraction. But why is the index of refraction all of a sudden 1.5 instead of 1? What makes that happen?
Because of the interaction with electrons?
Yes, the electrons that are free electrons moving everywhere, or?
No, that they are the electrons bound to the atoms composing the material.
Yes, exactly. So it's because when an electric field is propagating in a material, as it propagates, the dipoles in the material will try to oppose this electric field. So the act of opposition by the dipoles against the electric field is what gives rise to the index of refraction. And the reason why I'm saying this is that I really want to get to something simple, but it's because I want you to know right away we need that in the assignment. That's why I want to discuss it. But we can model the index of refraction, and there's something called if we look at the index of refraction in the material, the index of refraction in the material will always, it's very, very important, as a function of frequency. So this is a graph, a very generic graph of the index of refraction as a function of frequency in essentially any material. And what you do notice is that the index of refraction goes up until there is an absorption band, then it goes down, and then it keeps going up. So in a glass material, any glass material like the materials that we use in lenses, the index of refraction, we're always using a lens in the area where it's transparent. So we're always going to be using a lens in this area. We're not using a lens in an area where it absorbs the light, because then it would be opaque to that light. So for us, the index of refraction will always go up with frequency. So that means that the index of refraction is larger or smaller for a blue photon compared to a red photon. So which one is which? So the index of refraction is higher or lower in the blue?
It should be higher in the blue.
It's higher.
Yeah, higher in the blue, okay? So that's going to be important, okay? That's going to be important for lenses, okay? Because for lenses, that means that when you send a blue photon and when you send a red photon, the blue lens will see a certain lens, the blue photon will see a certain lens, and the red photon will see a different lens, okay? And that is something that you can estimate because of this behavior here, the fact that the index of refraction can be modeled there are models. There's something called the Sellmeier equations. Anybody has heard of the Sellmeier equations?
Yes,
Yep.
I've heard.
Okay, it's an equation that there are several forms of the Sellmeier equations, but the one that's fairly common is the square of the index of refraction is given as a sum of various terms. So the form that I'm using here is an equation that has 6 parameters: B1, C1, B2, C2, B3, C3. And now you're thinking, why would you do such a thing? Why would anybody care? Well, this equation, the Sellmeier equations, is nearly perfect for glasses in the visible to the 4th digit, okay? So it's been tabulated on various websites, and this is one of my favorite websites, refractiveindex.info, has all of these parameters for all glasses you can imagine. Okay, so it's a very, very, very useful resource because if you go to refractiveindex.info and I'm using here a certain glass, BK7, it's going to give you the index of refraction as a function of wavelength, and you get here the it's called the dispersion formula. So it's the index of refraction as a function of these parameters. So this is very, very, very useful when you need to do calculations for various lenses. Because for instance, let's say if if you want to know where the object is, where the image is for a given object, you can use 1 over di plus 1 over do is equal to 1 over f. So you've done that with Antoine. But at some point in your systems, you know, you're going to be working on your fancy microscope. You're going to be trying to graduate, and then you'll focus your fancy femtosecond pulse or your other femtosecond pulse, and you'll say, oh, how come the focal plane doesn't seem to be at the same place for the blue confocal laser or the red confocal laser, et cetera, et cetera. Well, you can estimate these things if you know the index of refraction of the various materials you're working with. Okay, so I find that this refractiveindex.info website is very, very super useful. So please take a look at it. I know that it's even worse than you think. I'll show you very quickly what I want to show you, why I love this website so much. I'm going to show you my screen. So if I go here, if you go to refractiveindex.info right here, and you can see my screen, right?
Yes.
Okay. If you go to, where is it? Yeah, you can get the data here, but what I'm looking for is, where are they? Where? I know where it is. Yeah, okay, I think, is it going to be here? No, that's not it. I can't find it. Data, material. You can click and get the equation for the index of refraction in Python, in C. You can get it directly with all the parameters that you want. Where is it going to be? I know it's, it's got to be here. No, how come I can't find it? Unit converter. Well, I know it's somewhere. How come I can't find it now? Well, I had it before, and I'll find it again at some point. But anyway, I know, maybe here? Well, can't find it. Okay, it doesn't matter. But I know it's somewhere. Okay, I'm going back to my slide. There we go. Okay. Okay, so all right. So I wanted to finish with this because I think it's a very useful resource. Okay, so we're done with the first part. I talked a little bit longer than I expected, but that was the minimum we needed to know to start working with lenses. So I suggest we take a quick pause because I'm going to go make myself a coffee. And we get back here maybe in 5 minutes, approximately 5 minutes, just so we move a little bit and get right back. Okay.
Right.
All right. See you in a few minutes.
What?
Pourquoi tout le monde est assis? Personne n'est assis.
Un peu, ouais.
Et quoi ça? C'est tellement intense.
All right, DJ Dan is done. Okay. All right, good. So, okay. So we're done here with that very first part, which was try to, yes, with all the music. Well, you're obviously taking a break from teaching Valérie. That's what you're doing. Tell your mom. Okay, so so that was the minimum I wanted you to know to get started, because now we're going to be working with components that manipulate the light to perform imaging. So the first hour was getting to know some of the basics. Now let's get down to business. So can you tell me things that allow us to manipulate the light? What are optical components that you know?
There are a lot.
Uh-huh. So generally, a few lenses. We know lenses, but aside from lenses,
mirrors. Yeah. Spatial light modulators.
A spatial light modulator. Yeah.
Polarizer.
Polarizer. Yep. Vincent.
Nonlinear crystals.
Yep. You guys are thinking of very complicated things. Filters.
Beam splitter.
Yep. Beam splitter. Dichroic mirrors.
Yeah.
Yes. Okay. So some of them we know very well because they're very because we work with them on a daily basis. You know, lenses, mirrors, dichroic mirrors. We'll see that in an optical system, the dichroic mirrors are very important. That's how we can illuminate through and get our fluorescence elsewhere. Filters, obviously, to filter only the light we want. Diffraction gratings that are tons of fun, but not used so much aside for our spectroscopy. And more optical fibers, which I don't talk a lot about in my course, but maybe at some point I should add a component on optical fibers. I think that'd be useful. Would you guys like to know more about optical fibers, or you think, yeah, I put light into optical fiber and I'm all set?
That's a good idea,
Yeah.
I think.
Yeah? Yeah? Yeah, you would say that you don't know much about optical fibers?
Not that much.
Okay. Okay, I'll see if I can add it at the end of maybe this course or the other course, because it's partly, yeah, okay. Okay, all right. So the one that is the most important for us when we do imaging is obviously the lens, okay? So there are various symbols to use, various symbols to when we draw it. Very often in a simple system, in simple software or simple figures, people will use just an arrow. And when the arrow is pointing out, that's a converging lens like this. And when it's pointing inside from the tips, it's a diverging lens. So you've seen that with Antoine, I know that. Okay, you have. Have you?
Yeah.
Yes? Okay. So the light, a lens will focus the light to the focal spot. So the light that comes from infinity is focused at the focal spot. And the light that comes at an angle, where's the light coming? Let's say the light comes from infinity, but at an angle. Where is the light focused?
The focal point.
The focal point or the focal... So it goes to the focal point when it comes parallel.
Mm-hmm.
When it comes, so if it comes at an angle like this, what do we call, where is it going to be focused? Okay, I'll draw it. So the light, if the beam is coming at an angle like this, where is it going to be focused?
At infinity?
No, like this. It's going to be focused.
The focal plane.
The focal plane, exactly. So we always refer to the focal point. The focal point is where a beam coming from infinity parallel to the axis is focused. But then there are a lot of points that make up a plane, and the focal point is on that plane, and all the other points on that plane are the beams coming from infinity, but at a different angle. Okay, and we'll calculate that in how many slides? In 14 slides. Okay, so okay, so what's important? Parallel rays, rays that are parallel. Whoops, rays that are parallel to the axis are focused onto the focal spot, and any other beam that is coming, any plane wave or group of rays that are parallel but are making a certain angle with the optical axis. So the optical axis, I remind you, because I don't think I have said it, but the optical axis is the imaginary axis in the center. So here we say that these beams are making, these rays are making a certain angle theta with the axis. So they are focused at a point here that is not on axis. Anybody knows what that distance is by any chance? Anyone who has maybe done some ABCD calculations at some point in life? I'm not looking at you, Emile.
I'm sorry, what was the question?
So we will see that a beam that comes at an angle theta right here, and enters a lens of focal length f, f, will be focused at a height here that's f theta. We'll see that in a bit. Okay, just a second. C'est quoi? Qu'est-ce que tu peux? J'entends pas. Non, j'en ai besoin. Okay. Okay. So this is for a simple lens, but in microscopy, we rarely work with simple lenses. We work with very complex lenses. So you have seen the simple thin lens, but there are very complicated lenses that are much more complicated than a simple lens. But we'll see that it's actually not particularly difficult, because we can simplify. We can take a complicated lens and replace it by what appears to be a simple lens. So for some of you, I'll force some of you to do some of these calculations, and others, well, you will not. But the point is that if we have our simple lens that is just something like this, okay, a simple lens has a focal distance or a focal point, and that's it. Well, a more complicated lens will have a certain thickness and will have a certain curvature. And did you see thick lenses with Antoine? No? Okay, good. But the point is that in the end, what you need to remember is that we will be able to describe any complicated lens by an equivalent thin lens. And we'll just say, I'm not doing it now, but I'm telling you that the answer will be that we'll describe something called a principal plane.
Mm-hmm.
And the principal plane is going to be, it's as if we're going to say this complicated lens, it's as if a thin lens was starting here at this principal plane, and magically the beam appeared at this output principal plane, and the focal point is always one focal distance away from the principal plane. So what is it we need to remember about this? You know a simple lens, and the simple lens is the only thing we really want to understand very deeply, because a complicated lens can be simplified to a thin lens. So if we understand the thin lens, we'll be fine, okay? So just so you understand that we don't need to understand complicated things to understand the microscope objective. We'll just say, yeah, well, it has a bunch of things, but in the end, I look at it and it's a lens, okay? So we'll discuss that. Okay. And we'll prefer our very simple description for now, and just remember or appreciate or please note that we'll have our thin lens that's here. It has a focal point that's one focal distance away from the center of the lens. The focal distance on the other side is always at the same distance if it's air on each side. And the principal planes and nodal planes that I'm not discussing yet in a simple lens are in the center, okay? So everything is in the center in a thin lens. But when we need to understand a complicated lens, then these principal planes and nodal planes will be moved around, okay? But in the end, the concepts will remain the same, okay? All right. So if we want to describe what happens to rays as they enter lenses and materials, we're a little bit, we know a little bit, okay? We know a little bit of physics. We know that the refraction of the beam will curve the rays. Okay, so that you've seen and you know what's the law of refraction? Anybody can tell me what the law of refraction is?
Snell's law?
Yeah, Snell's law. So what is it? It's
N1 sine theta 1 equals N2 sine theta 2.
Exactly.
Yeah.
Yep. Okay, so that we know. Okay, and you remember that from high school and Cégep and Antoine, right? Everyone knows that. Okay, so the point is by changing the index of refraction, we can change the orientation. And if we adjust the curvature, then changing the shape of a material will change the incidence angle. So then we can curve the beam in any direction we want. Okay, so for a lens, okay, that we've seen, okay, you have seen this with Antoine, but the light okay, we will remember these three, we call them cardinal rays, okay? We have a ray that comes parallel to the axis, is focused, will go through the focal spot, okay, the focal point. A beam that goes through the focal point on the other side will come out parallel, and a beam or a ray that goes through the center of the lens is not modified. With this, we have enough to do what you have done before, that is find the image of an object. So you guys knew about these three rays, I assume? Yes?
Yeah.
Done that before? And you've done that with Antoine, have you?
Yeah.
Yes, no?
Yes.
Okay. So that means just by drawing figures, we know where the image will be. Where is the image of a given point? How do I find the image of a point? Well, I draw, what is the definition of an image? An image, that means I have a point here, and if I get an image, that means that all of the rays that leave this area here will go to the same point here. So I have several rays that can leave this point here, here, here. I have different rays that have the same origin, but go at a different angle, and they all go to the same point, and they all cross at the same point. So if they cross at the same point, what does that mean? That means that any light from this point will be imaged at this point, okay? So as long as I find two rays that are crossing, if I draw, I can take this, I can take a point, let's say I want to draw it for here. I'll do it with blue beam, okay? So if I want to know the image of this point, it's actually very easy. I need two rays. I will draw one that's parallel, and then it's going to go through it's going to go through the focal spot, and then I will have this here that will go here. Schluck. So I didn't draw my B properly. Okay, so they cross here, so that means the tip of my B is imaged here. Okay, so my drawing was not the best. Okay, so far so good.
Yes.
Okay, so we know the math for this. We know that 1 over D plus 1 over O plus 1 over I is 1 over F. That we know. Okay, so we know how to go. We know if we have a certain image, a certain object, we know where the image is. Okay, but we may want more than that. Okay, sometimes. Okay, we know that there are several ways to get the magnification of an image. Okay, if we can draw the rays, okay, if we can draw the rays of our system, then by drawing little triangles, okay, we can draw a triangle here, another triangle here, and we can very quickly get that the transverse magnification of these two objects, of this object and this image, will be given by the distance of the image divided by the distance of the object. That's going to be exactly the same as the height of this image divided by the height of this object. Okay, this is a little bit boring and not so much fun, because we know object and images, that's great, but that's not what we really want to know. What we really want is we would like to know maybe how to get the focal length of a certain lens, or how to get the focal length of a given system, or even better than that, get the light anywhere in our system. So we can see if the light is blocked by something in our system, if the light is maximum at a certain point in our system, if we have an other intermediate image in our system, etc. So when we draw the rays, okay, that's the thing I'm trying to show you here. When I draw the rays like this, we say they start from a given object, a given point, and they're imaged at another point. Wait. So in this case, we know that we have an image, but what happens to the light in between here? Okay, we've taken key rays, but we would love to know what happens to the light in between. Okay, because maybe the lens is too small. Maybe I have another intermediate image somewhere. So to do that, we need to go beyond the equations for object and images, because the laws that we have, I think it's called the Gauss's law of imaging. I'm not even sure, but this law, the law we know here, 1 over dO plus 1 over di is 1 over f. That's object image, but we would like to know more. Okay, for instance, there are various ways to get the focal length, but how did we get that? You know, how was this equation obtained? And there are tools for that, and I really hope that you guys will accept one problem in the assignment on this, but they're called the ABCD matrices. Has anyone, aside from Emile, has anyone heard of ABCD matrices?
Yes.
Yes?
Mm-hmm.
No? Okay. So if I say matrix, are you guys scared, or are you okay? No, it's okay. Matrices? Okay. Okay. So the mathematical description that we would like to use, and I have 2 slides. Okay, the point is not to make you experts of light propagation, but the point that I'm trying to make is that you may want to know object image, you know, where they are, but with this formalism, this ABCD formalism, then you can take a ray from anywhere and propagate it anywhere, even when it's not an image plane. Okay, so we had object, image, so we call them conjugate planes. But if I have a given ray that I know is starting at a certain height, so I have my axis here. If I start at a given height and I come at a given angle, I have a certain ray like this. So it is possible to calculate how free space, a lens, more free space, mirrors, many other things, it's possible to calculate how they transform this ray. So the formalism is called the ABCD formalism, or ray matrices, or Gauss matrices. And we have, I'm skipping, I usually teach this for a few hours in my optics class, so I will not go into details here, but the point is that we consider a ray, when we want to describe a ray, we describe its height and its angle. So if I have a ray that's at a given height here and goes at a certain angle, I have this R theta or R alpha, doesn't matter. It will be affected by free space. Free space is represented by a given matrix. We say A, B, C, D. So the matrix for free space is 1D01. So if I have a certain ray at a given height, R alpha, at a certain height and a certain angle, then free space, I take I take this 1D01 matrix, I put it here, so I would do 1D01, and the resulting ray will be, in this particular case, if I'm looking at a matrix that's 1D01, then I'll have at the output a ray that will be what's it going to be? What is it going to be? It's going to be R plus D theta, and then 0 theta. Did I make a mistake? It is so clear when I type it. Let me do that again. Okay, like this. R plus D theta, theta, like this. Did I make a mistake?
No.
Okay, good. So the reason why I'm showing this is that if you have a matrix that can represent, let's say, free space, a dielectric, a lens, a curved mirror, any other thing, then you can propagate rays everywhere in your optical system. Okay, and there are tools that can do this. Some of you may know Zmax. Zmax is the standard in the field, but it's very expensive. Oslo is free, but is not that good, in all honesty. And I've just learned of Code 5 recently. Code 5 apparently has an academic license that is quite cheap. It's essentially free. It's like $50, and these software will you can put all of your optical components in your system everywhere and get the calculated rays in all points in your system. So I just learned actually a few weeks ago that Code 5 is very cheap. So it's expensive, but not so expensive for academia. So this is actually a good option. And I had an old version on MATLAB of software that I made myself, but I just want to say for anyone who knows Python that I have a version of I have my own little ray tracing system, and if you want to install it, you can use that in Python, and I'll just give you the example of what it does because I think it's a useful tool. But you can everyone sees my screen? Yeah. Okay, so I made a small ray tracing package that does just what I described here: matrices, rays, blah, blah, blah. And it will calculate the rays everywhere in your system. So if you have an object, you have a lens, then you can know where the image is. And there are tons of things that it can do. One lens, many lenses, lenses that are finite with a finite diameter, and even a simple microscope system, etc., even very advanced things like calculating what's called the chief ray or the marginal rays. So if you're interested in these calculations, I would highly recommend that you take a look at this ray tracing package, and I'll give you a link in a few seconds. But yeah, that's what I wanted to show. When we discussed that with a thin lens, we just say it's whatever it is and it has a given focal length. But real lenses in real life are not like that. They have a certain thickness, and then the focal point. Let's say I have a real lens in the laboratory. So this is I'm not sure if you can see well. I'm gonna try to go like this. Can I do this? I can't do that. Maybe, yeah, okay. So if I do this, aha, okay. So I'm assuming now that you can see this. It says that this is a certain lens that from Thor Labs called the AC Acromat 254, so the 2.54 millimeters, so that's a 25.4 millimeters, so that's a 1 inch. 50, so that's a focal length of 50, and it has a it has a coating for visible light. Okay, why am I showing this? It is a lens that has an effective focal length of 50. That's what you see here. Can I do? Yes, okay. Sorry. So it has an effective focal length of 50 millimeters, but the focal point is not 50 millimeters after the last, sorry, the last surface of the lens. Okay. Okay, so it's not 50 millimeters after, and knowing these things, so in this particular case, this thick lens, if we try to figure out where these principal planes are, then we get that the principal plane is essentially at the interface on one side, but it's very much inside of this thick lens. Why am I describing this? Why am I even talking about this? It looks like it's a very tiny little detail, but it's not. When you're in the lab and you're making your systems with your lenses, your real lenses, the focal distance, the focal spot is not always one focal distance after the last piece of glass. Okay, and knowing these things, it's not difficult. You can just calculate it, or you can look at what they give you. But my point is that with this very simple package, it's actually very easy to calculate where they are. And I've double checked even the values with Thor Labs, and it works perfectly. So what's my point? My point is that with simple matrices, it's possible to calculate all the properties of our optical systems and calculate the rays everywhere. So some of you will want to do more, and some of you will say, oh, just knowing that it exists is fine for me. So is there anyone here who would be interested in doing calculations for their optical systems, for instance? I know Valérie maybe. Vincent? Yeah. Shadi?
I don't have an optical system, but I need to have one.
Emile, you probably have your own tools to do that?
Yeah. Well, actually, I don't have to modify the microscope, so.
Okay. And Julien?
I also don't have, I will not modify.
So anyway, for those who would want to know more, I guess you can come see me, but I'll give you more references, but I have a small book, small notes that I have written that I use in my more advanced optics classes, and all this matrix formalism is described in details here, unfortunately in French again, but everything is described here in this, I would say, relatively simple chapter. Okay, so for anybody who wants to know more about the details, I would highly recommend that you use software to perform the calculations that you need. Okay, so I'm going back to my slides. Yes. Yeah, there you go. And this, all right, good. Okay, so yeah, oh, I forgot, too late. But I'll give you the link for the package, but if you want to use it in Python, it's fairly simple. You type pip install ray tracing, and then all the examples are available. Okay, good. Okay, so we know how to get the ray everywhere in our system. There's when we do imaging, unfortunately, there's one thing that we need to know when we start, and it's I need to include this right away. It's not true that a beam is focused to a point. In geometric optics, we say a beam that enters a lens is going to be focused to a point, but we know it's not true. Okay, we know it's not true because because we know the limit, the resolution of a microscope is not infinite. So we can't see all the fancy little details. And the reason for this is because a beam that enters a finite lens will diffract. And the simplest way to describe this is to say that let's say if you had a perfect lens, or a perfect, if you knew that a spherical wavefront was, if you had the full wavefront, yeah, that's the way I can say that. Is if you had the full wavefront for a beam, you could say, I know from this spherical wavefront, I know that the original beam or the original source was from this point. Okay. But for this, we would need to know the wavefront. We would need to know the wavefront from on all points around, everywhere. So if I have the full wavefront, I can say, oh yeah, it's coming from here. But in a microscope, that's not what we have. In a microscope, we only have a finite view of the beam. So we don't have the complete wavefront. So if we had everything, we could say the beam is coming from here. But for us, because we only have a limited view, then we'll have a limited resolution, okay? And this is going to be given by the numerical aperture of our lens. What is the numerical aperture of a lens? Anybody can tell me in their own words what the numerical aperture of a lens is?
Yes, and it's the lens ability to collect the light.
Yes.
I mean,
so
how much the light is collected by lens.
So it's a number, and it goes from 0 to
1.
Yeah, 1 in air. Yep.
Mm-hmm.
More? Anybody can tell me more? Nope. Well,
and the more is the numerical aperture, the better is the resolution, I guess.
Yes, that's correct. Okay, so the best way to describe this is that the way you have to remember this is if we knew, if we had the complete wavefront, we would look, if we could look around, completely in a circle around the point, we would have the full wavefront and we would know exactly where the beam is coming from. So if we had a numerical aperture that was very large and we could look around the point so much that we had the full wavefront, then we'd have a great resolution. So if the numerical aperture is large, we approach the best resolution. And when the index, not the index, but when the numerical aperture is smaller, then we only see a small cone of light, and therefore the resolution is limited. So think of this, the definition for the numerical aperture is the index of refraction in which it is used times the sine of the angle. So if you have a lens like this and this, then the sine, oh wait a minute, is it 1, 2? Is it half? I'm always confused. Help me here. Is it going to be half or the full angle?
It's the half angle.
Yeah, it's the half angle. Okay, good. All right. So did you discuss this with Antoine?
No.
Okay, good. Okay, so it's the half angle here that's going to be, so I wrote theta, but that's really u, or theta here. And so the numerical aperture can go from, okay, just a second, I'll give some time to my daughter so that she can play. There you go. YouTube. Okay. An hour. All right, good. Management. Okay, there we go. We're back. We'll stop getting messages. Okay, so the numerical aperture is the cone of angle, the angle of the cone, and the larger it is, the better the resolution. The number you have to remember, in microscopy, we always talk with numerical aperture. Do people here do photography, maybe?
Sometimes.
Sometimes. So in photography, when you buy an expensive lens, they will talk in terms of the F number. The F number is the focal length of the lens divided by the diameter. The F number and the numerical aperture are related. If we want to have a very good resolution, we want a very small F number. If we want to have a very high resolution with an NA, we want to have a large NA. So the NA and the F number are inversely related. So F number is 1 over or half of 1 over NA, or 1 over twice the NA. Okay, this is important to know because this will give us the resolution, and that's why, for instance, an objective with a very high NA or a very large NA is more expensive than an objective with a smaller NA. And for us, the part that we want to know is that the resolution of our system is essentially the lambda divided by the NA. Okay, so 0.6 times lambda divided by NA. So that's going to give us the resolution of our system. And if you notice, I always get confused with DNA because I prefer to discuss this in terms of F number, because if you use the F number, if you use the F number, this equation here is just the F number times lambda. So when you discuss the resolution of a lens and you have its F number, then the resolution is very simple. If a lens has an F number of 10, well, the best you can do for the resolution is 10 times lambda. So the F number is a very, very, very convenient number. Whereas with the NA, you have to say, oh yeah, my NA is 0.1, so 1 over 2 times 0.1, that's 0.2, 1 over 0.2, that's 5, so that's 5 lambda. Yeah. So in F number, it's a very convenient measure of resolution. Okay.
Isn't the resolution dependent on the detector?
Yes. Okay. The resolution we're discussing here is the best that optics can do. So even if you have a detector with super tiny pixels, super excellent pixels, then the wavelength of the light will limit you to this limitation with, let's call that regular imaging. Okay, because I discussed there are some techniques, super fancy techniques called STED microscopy or palm microscopy or storm microscopy that go beyond this. But this is what optics can do. The detector could also be a limiting factor, and that we discuss in the third course, I think. Right now, we're just getting our light from our object to our detector, but we haven't detected it yet. Okay, and will the detector in a real situation, you will want your detector to you will want your detector to be better than this, so that the final limitation is not your detector. Because if the detector had a pixel that was worse than that, then that means you could do better if you had a better detector, but you'll never be able to do better in a standard imaging system than this limit. Okay. All right. So, okay. This you've done, so I'm not going to redo it. Okay. There's one thing that I want you to see, because we need this to understand our microscopes. So you have seen object, image, and you've done that, and you know that you can use this equation that you've used before, right? Okay, so this is a known technique. Okay, but did you talk 4F systems?
Yes. Yeah.
You have? Okay, good. Excellent. So this system with conjugated planes gives you an object and an image, but the magnification depends on where you put the object, because the image is going to be at a different point, and the ratio of the distances is the magnification. So there is a system called the 4F system, where if you put two lenses and they're separated by the sum of their focal length, then we can do the calculation and show that if you put an object at the focal plane of the first lens, it will appear at the focal plane of the second lens. Okay, and the magnification is always going to be the same. Qu'est-ce que tu as, Lulu? Oui, je suis encore en train d'enseigner. Oh, je vais avoir fini dans pas beaucoup de temps. 2 minutes? Non, pas 2 minutes. 1 seconde. 1 seconde et 50 minutes. OK? Puis je vais aller te voir après. Oui, je vais aller te voir après, Coco. Bon. OK. Sors, Coco. Essaye de ne pas frapper la ballonne, s'il te plaît. Non, non, fais pas ça. Lulu. Excusez-moi. Lulu. Lulu, il faudrait que tu sortes. Lulu, s'il te plaît. Lulu, faut-tu que j'aille te péter la ballonne? Bon, merci. Tu peux fermer la porte. C'est gentil. Merci. Oui, si tu as faim, ben, va te chercher, prendre une collation. Bon, et voilà. OK. C'est mon correcteur pour vos devoirs. OK. Donc, Okay, so why is this relevant? Why am I talking about this? The magnification in a 4F system is always the same. Okay, so if I put an object here at the focal plane, the image is always going to be magnified by the same amount. That's different from a system with a single lens. With a single lens, if you put the object at a certain distance, you always get an image, but it's going to be magnified differently depending upon where it is. In this 4F system, if you put an object at the right place, you get an image at the right place with always the same magnification. The reason why this is important is that that's the basic building block in all microscope systems. Okay, so this 4F system is also called a relay. Okay, and the magnification is always given by the ratio of the focal length. So here, okay, if I have a focal length of f1, okay, this one here is f1, this one is f2. So if the f2 is a longer focal length, then this is going to take this object and make it a larger image. Say if this is 100 millimeters and this is 50 millimeters, you'll get a magnification of 2. Okay. If you look in more details for the experts here, but between one focal plane and another focal plane, there's what's called the Fourier plane. So if you have, I told you that there's an object here, it makes an image here, but in between, at one focal plane away from the first lens, there's what's called the Fourier plane. For some people who will design systems, this is important because that's where you can do Fourier filtering and do things that are relevant to your imaging system. An SLM, a spatial light modulator, is actually put at the Fourier plane, usually in an imaging system. Okay. The point is that for people using microscopes, you need to be able to recognize these 4F systems or the relay systems. That's how you can understand where the beams are and where the important planes are. For experts who need to build them, this Fourier plane is sometimes important because you can apply filtering techniques and you can put an aperture here to filter a beam that's not as clean as you would want, etc. But for now, let's just focus on this complete plane, okay? And the 4F system is also called a relay, and it's the building block for all microscopes. Okay, the Fourier planes I don't need to discuss, but what I want to show you is if you look at a microscope, microscopes sometimes appear to be complicated, but in the end, what do? What is a microscope? A microscope is if I were to ask you, explain to me what a microscope is, you'd probably say, oh, it's a bunch of lenses and it's complicated. And well, why do we have a microscope in the first place? You know, why do we even make microscopes? Because, for instance, if I wanted to look at this pen, I can just put it close to my eyes, and I'll just look at it. Or I can just put it directly onto a camera, and I could image it. So the reason why we make a microscope is that we want to take what's at the object plane and bring it to a camera, because we cannot put the camera directly onto the object. Okay, if we could put the object directly on the camera, then we would. Okay, so all we're doing in a microscope is to take the light from the object and put relays and various things in the system to bring it to another plane where we put a camera. So that's really it, okay? So when we have, okay, so if you look at the slide that I have on the screen now, everything may look complicated, but what's the point? The point is that okay, I have something that's very small here, and it is actually smaller than my camera. Let's say I'm interested in looking at a square of 200 microns where I have several cells. Well, I don't have a photographic film or a CCD camera or anything that is that size. I only have large cameras that are, you know, a centimeter or an inch. So I need to take the light that's here from the object, make it bigger, and bring it to a point where I can put a camera. But the cameras are big. So if I were to just take whatever is here and keep it the same size and bring it to the camera, I wouldn't accomplish anything, because I would have a tiny little square that's 250 microns, for instance, but my camera is 25 millimeters. So that's why we relay the information from the object plane, make it bigger so that it fits the camera, and then we can look at it. So a microscope is only a bunch of relays together. It's just to take the light from, it's just to take the light from here and bring it to my plane where I have a camera. And often we can't do that in a single shot. So we'll have a relay, another relay, another relay. And because microscopes are built to be versatile, we'll have various relays where we can insert things and filters and dichroics or other cameras or another beam, and they will have various steps or various relays and various points. If you look, for instance, at what we have here, okay, what we have on the right on this figure, then we put a certain beam splitter at a certain point in the microscope. Okay. All right. So.
Okay, I'll stop you.
Yeah.
I think you're lagging.
I am.
I don't think it's me.
Yeah,
or perhaps it's me.
No, it's not you. It's
okay.
Okay. So
sometimes you just stop talking.
Yeah.
Oh, that's no good. Okay.
It cuts a little bit.
Let me see. Maybe the kids are playing Fortnite on the computer. Okay. Well, it's already been 2 hours and a half.
But now it's fine.
Yeah, it's fine. I'll just. Well, I'm essentially done on the important things. So let me. We need to wrap this up because it's been a long day. So my point. I always have a point. Okay. A microscope is a bunch of relays together, even the super complicated ones. If you look at this microscope, it appears very complicated. But when you look carefully, you will see that, for instance, you have a certain object, then a lens. Well, if there's an objective, there has to be another lens. Oh, there's a tube lens. A tube lens is here, et cetera, et cetera. You always, in all microscopes, you have to, when you look at the microscopes, if you want to deconstruct them in your head, you have to find the pairs of relays. Okay, that's going to be the key to understanding a microscope. The only part where it's not quite what I just said is for the illumination arm of a microscope, which is what applies to Valérie, by the way. Okay, an illuminator is not quite a relay for a bunch of other reasons that that I will not discuss now. Okay, so in the end, it's always going to be lenses and relays to a given imaging plane. Okay, let's see. That's the point usually where I talk about details, but I feel I've talked enough. I don't want to talk more. Yeah, I'm looking at my slides. I'll do that at the beginning of the next class, okay? Because we have just very basic, we have a basic understanding of the building blocks, and the other things that I have are about aberrations. And you need to know, but I think at this point, if I start talking about it, people will not be, you know, it's been 2 hours and a half. It's too long already. So I'll stop. I'll give you all the slides, but I'll give you small problems that you can do just so you integrate a little bit the things that we have discussed here. So if I just to double check, can anyone here write stuff in Python? Can anyone do Python coding? I'm assuming not. Python, Vincent, Python?
Well, it
Cut. I
Oh. Hello. Okay, I completely missed everything in the last 10 seconds.
For the we can hear you now.
Okay. Yeah, but
Maybe.
Yeah, it's let me. Allô?
Ça va, Vincent?
Allô? Je suis revenu.
C'est bon.
Okay. Hello.
Hello.
Hi.
Okay. So I don't know what's going on, but that's certainly a good sign that it's time to stop. But so Python, can anyone do Python? I didn't hear the answers. Yes. Yes.
Bit, yeah.
Yeah. And Shadi, you'll learn. It's easy. It's like MATLAB. It's like MATLAB, but it's not MATLAB. But you'll see. It's but I have an assignment that I'll give everyone. It's very simple. Oh, can you hear me? Aha.
Thanks, because my room is a disaster.
Oh, no. It's
Okay.
really interesting.
Ah, come on.
Attends, ce sera pas long, j'ai presque fini.
Can't be worse than this.
Okay, no. Not that bad.
Uh-huh.
Oh,
All
no, you were back.
Okay, so I'm back. I'll give a small assignment. It's an easy assignment. It's just for people to get used. It is simple. It's always simple. I expect that it's going to take you
a day,
a little over an hour,
a week,
maybe a little over an hour. That means at least 5 hours.
It'll be fine. It'll be fine. But it's just to move things around and get numbers. I used to give the course in a more qualitative manner, and in the end, people just couldn't get the resolution of a microscope. They couldn't say where the object images. Where do you put the camera? Oh, I put the camera here. Well, you need to put the camera at the image plane. Where do you put it? Where is that image plane? So it's simple things because it's an imaging course. So I have simple questions. I'll send that to you very quickly. And if you have problems, then you can, hey, you could burn your camera. You shouldn't be doing that.
I'm not pointing at the captor.
Oh, okay. All right. So so I guess that'll be it for now. And I'll finish. The other things that I have to say anyway are practical aspects about imaging. So so for now, we'll stop. And this was probably a little bit of a review for most of you. Yes, no?
Yes.
Yeah, Valérie? Yeah, no?
Yeah, but
I learned
it's
things.
fine. I needed it.
Yeah.
Okay, good. Julien?
Yes, the same.
Okay, good. So, all right, I'm sending you the assignment, and then we can meet again on Friday. Are we all right?
Mm-hmm.
Yeah.
Dynamite. I'll send you also a lot of resources if you want to know more, other courses that are online, material, reading material, references, etc., etc. Okay?
Okay.
Excellent. So I'll see you Friday.
Right. Thank you.
Have a
Bye.
good day.
Bye.